Okay, folks. So we're going to jump right in because I'm late because I went up to the observatory to bring up new stuff. You have a homework due on Monday. I have yet to hear a single question, so I assume that you're killing it.
Yeah, we are.
And you've definitely not looked at it, right?
Nope.
Question?
Can you answer now?
Yeah, we can answer a question. A clarification question, sure. I'm not going to work through the problem with it.
Okay, so the chat
Mhm.
PTs,
Mhm.
they kept giving me like no, like the answer no for that question.
Mhm.
And you said to just keep redoing it.
No, ask a different question.
Different question?
Yeah, change your question
Here's my question.
until it gives you the right answer. You see?
But you see, wait, so like a different, like a revised question? Revised? Yeah.
So as you ask it a question and it gives you garbage, change your question until it gives you the right answer.
Oh, okay. Yeah.
Does that make sense?
Yeah.
Okay. And then you'll note that lunar observations, if you were at the observatory, I think everyone was at the observatory. We didn't even see the moon until like an hour and a half later, right? So I gave you this, and the funny thing about this is it asks for questions like, where's the Terminator, and looking at things like that. I'm like, well, it was fucking full, bro. What am I supposed to do? So you, in fact, anytime you go to a public observing night, you will see probably both the moon in different phases and deep sky objects. So what I'm going to do for you is I'm going to give you this one, and I'll print out the other one. I forgot to do that today because I've been all over the place. And you'll just hold on to them. And throughout the semester, you fill them out. At the end of the semester, you give both of them back, filled out with all your knowledge. Okay? Is that fair?
Yes.
You'll probably get 100 on them because you just have to arrive and be. You know, don't make the moon red. Okay? Questions? Okay. So let's do this one. We were talking about the 4 planetary processes that we see in planetary geology and terrestrial planetary geology. On the left-hand side is a mountain, and it's also a volcano. That's the first planetary process we're going to be talking about today. Anyone know what mountain this is? Mount St. Helens. Correct. How do you know it's Mount St. Helens?
Big old dome on this.
Yeah, because literally exploded the shit out of it.
Yeah.
So that's before and after. Like the worst makeup commercial. Also, by the way, sorry to interrupt. This is the last page of your last lecture tutorial. If you look at it and you compare it to how shitty these ones are, the problem will be a lot easier. If you were really confused by the last few questions in the last lecture tutorial, this is your solution. I'll give you that later. Okay. So we're going to talk about volcanoes. What else do you notice about this picture? One has snow, the other doesn't. Very good. What happened to the snow?
Melted.
There's more water.
Yeah, it melted. It also got exploded, so it also could be just a different season. So maybe that's not it. Anything else? There's no vegetation. So in fact, all of these trees were destroyed. When something like that happens, not only do you get an explosion, you get something called pyroclastic flows. And these are gigantic waves of hot air, essentially, super heated air that are moving very quickly, and they burn and destroy everything. So when an earthquake goes off and you're like, oh, that's so cool. Just wait like 30, 40 seconds and then you're dead. You don't even have to touch the lava to die from a volcano. This one is incredibly interesting because there was a photographer who I think was studying or doing something for the parks department, and he was taking photographs. This is like the 70s, and he realized this thing was going to go, and so he took photographs. And the very last minute, he like covered his camera and laid down on top of it. He died, but all the photos survived.
I saw it. That's
Good. Yeah, it's pretty cool, right? I don't know.
No.
Okay. Okay, and that's what it looks like from very far away. So 10 seconds into the eruption, 42 seconds into the eruption, 52 seconds into the eruption, and 60 seconds into the eruption, the whole mountain just disappears.
But just within a minute. basically.
Yeah. You fucking crazy, right? Okay, so we'll talk about this. Volcanism. It's really important. We'll talk about it when we talk about tectonics, to recognize that we just are living on a giant ocean of magma, and we're just on a little rock boat. And that rock boat gets moved around a lot. Therefore, yeah, sure. Okay, so here's our 4 processes again. What was the definition of volcanism? Not using the word volcanism.
Magma.
And magma, that is not a definition, but you're close. Lava is also not a definition. We want a definition, folks. Rock. Not a definition. Magma coming to the surface. That's the idea. Okay. Yeah, that's a full concept. Right? Like that full concept? Okay. So we're gonna talk primarily about volcanism today, and we have lots of fun videos. So. Questions about this before we get started? One thing I'll remind you of course, is that the viscosity, the goofiness of the lava itself tells you a lot about the types of volcanoes. So lava plains is what we saw on the moon. Those were the flat, dark areas. And shield volcanoes, what's an example of a shield volcano? Here on Earth? What's that?
Hawaiian Island.
Correct. The Hawaiian Islands are shield volcanoes. That's very runny lava, shallow siding, that moves before hardening. And what is a stratovolcano example? What? Mountains is, these are all mountains technically. Just heard it. Mount St. Helens. Mount St. Helens is a stratovolcano. And in fact, you can tell it's a stratovolcano because. Nope, look at it. Tall is not a sufficient quantity. It's close. Steep. So tall and short base. Because we can have very tall but flat base. Right? Hawaii is in fact the you have like a 15,000 foot mountain on Hawaii, but it's very wide. Okay, so here you have a stratovolcano. You can tell by the peak here. You can also tell because these types of explosions, these types of eruptions are explosive. So when the viscosity is very low, you get trapped gas. And everyone knows what happens when you take, say, a can of like dust off, and you put it under tremendous heat.
What?
You ever done this?
Yes.
Why would I?
Yeah, accident.
Close. What? Well, okay, you ever take like hairspray and then take a lighter?
No, that's very dangerous.
Okay, all right, and we're gonna talk about it later. Okay.
No one-
Good job being safe, not recommended by the universities. Okay,
But it is recommended by Dr.
okay, so no. So we're going to release trapped gases every time that we have an eruption. But let's keep in mind that the word eruption in your mind evokes this idea of explosion, and it doesn't always have to be that way. Right? If you have like a seafloor crack that opens up, magma comes out, you can still have gases come out. They're just gonna dribble out. Okay. We did that. Okay, so this is another example of shield volcanoes. We didn't get to do a lot of it here. When we're looking at Venus, we take 2 different types of data. We cannot see the surface with our eyeballs, so we have to use radar data, and that is the background image here. This is radar data. And then the foreground image, the one in color, is thermal infrared. So this is like what you would use if you're playing COD and you have like the heat vision. This is literally heat vision. So you can see the hottest part of this is at the top of this mountain. Does that make sense? Okay. There was supposed to be something already here, but I guess it's an animation now. We talked about the Hawaiian seamounts. And this is your example of the Hawaiian seamounts. Has anyone been to Hawaii? So if you've been to Hawaii, you've probably been to which one of the islands?
Maui?
Maui. Okay, so Maui's over here. I mean, this is nice. It's beautiful, right? Beautiful island chain. The size of this here, right? So this is like 50 kilometers, about 50 kilometers across. The whole thing, maybe 300 kilometers. But this is really the beginning of something totally different. And what you see over here is the stuff that's over the water. And all the way back here are ancient islands. Okay. This is what is the name of the seamount? It's like a mountain ridge, but it's underwater. And I forget what it's called. But essentially what this means is that over here you have the newest island. I don't know how to pronounce that. I'm not going to attempt to butcher it. What's happening right here is there's a hot spot in the crust. Essentially think of it like a weak point. And hot magma is coming up from the same point in the crust. So there's like a column of hot material. And it melts whatever crust is above it. But the crust is moving. We'll talk about that when we talk about tectonics. So here's these Hawaiian Islands. Okay. I'm going to ask you, think about this for a few seconds. Don't just shout it out. Which direction is this plate moving? Should I rephrase it? Anyone lost? Okay, at the very bottom here, this is where a brand new island is being made. This is the largest island, Hawaii, because most of it's sticking up out of the water. It's created by volcanism. There's a big hot spot right here where magma comes up to the surface. However, these are older islands. And in fact, you can see the dates here. 0.0004, very young. 4.9, very old, right? And what's happening is, as volcanoes create more material, right? You get this brand new volcano, then the plate, which is sitting over the hot spot, moves. And as it continues to move, you get new islands in every location. So this is a chain of islands, most of them underwater now, that's formed all through the same process. And so in fact, if you look, you see there's a line like that. And my question is to you, which direction is the plate moving? To the left, this way?
No.
Wait, that's all right.
This way?
I'm saying there's only one.
Right down.
Yeah, so you're right. Over to it's dragging like someone put a Sharpie on a piece of paper. Yeah. Make sense? What happened up there? Something. Is there another plate? Very good. Close. Right way to think about it. The plate changed directions. What? So the plate was going straight like this. Okay, it's heading up that way. And then it just changed directions. That make sense? Why? They're all bumping into each other. There's no like, it's not like you're driving around with a car. It's like, yeah, you like bumper carts, but there's no space between bumper carts. So if you bump into everyone else, right, you just move everyone else on the entire. We'll talk about tectonics in a lot more detail, and I'll show you all of the plate boundaries. It's fucking awesome. Okay. So that's these guys here. We talked about the best planet in outside of the Earth, which is Olympus, which is Mars, and Olympus Mons. This one's just so cool. You really got to take this in. Think about it in great detail. This one's so tall that when you stand on the top of it, you're standing basically outside of the atmosphere. So most of the atmosphere is way, way down here. And like you think, oh, I go up to Mount Everest and I need breathing apparatus. This you're like sticking out of the atmosphere. And you look around and it's flat. I don't want to go to Mars, but if I did, that's where I go. You couldn't ski there, it'd be very boring, but it'd be kind of cool. You know, just the thought. Questions? So everyone understands shield volcanoes, stratovolcanoes. Here's the size. Bonkers. Has anyone been to Arizona? Yeah, so you get like, what? Yeah, okay, well, there's like Tucson and Phoenix, right? They're all like, you can have whole cities on the top of Olympus Mons.
So would Olympus Mons be considered a shield wall?
Yes, yeah, so that's exactly the point, right? And in fact, when you look at the topography here, okay. This is the entirety of Olympus Mons. There's a little cliff edge all the way around where it kind of like falls off. What else do you notice about this region of Mars?
Like two small craters?
Two small craters, good. So maybe right here. And right here.
Yeah.
Anything else?
What else different?
The soil color is different, right? Yeah. And in fact, so this is the caldera. This caldera is enormous. This would eat all of LA. It's all just magma. And we'll see really similar calderas when we look at the tectonic sections on Earth. But one thing to keep in mind here is, why are there no craters?
It keeps erupting.
But
And
is it erupting?
wouldn't it just erupting and then it would smooth everything out? Like,
Okay. Second part of that's the one I want, right? It's the fact that you're absolutely right. As more lava comes out, it smooths it out. Now, we don't know if the distribution of asteroids, impactors, is all at one time, or if they're evenly, right? So we don't know if it is or is not currently erupting, but what we do know is if it did erupt, it would have smoothed away anything that's old.
One, is Olympus Mons still an active volcano?
That's the question. We don't know. I mean, it's not erupting in the same way we think of eruptions. We're pretty sure it's geologically dead. We sent a seismometer called InSight. It landed on the surface. It detected a couple Mars quakes, but like not a lot. That's how we tell the interior of a planet.
Do you guys have like a simulation of what a hypothetical eruption would look like if it were to reactivate, or?
You want to see it?
Just as.
Yes. Okay, hold on. All right. To imagine what this would look like, it's quite simple. You just go to Hawaii.
well, wouldn't it be different since the atmosphere is different? Like the,
Lava don't care.
but wouldn't it just kind of float away without the atmosphere? Or
Lava heavy.
lava heavy?
Lava heavy, heavy. Let me show you how heavy lava be. Okay. It is full screen, right?
Lava heavy.
You better go faster, video. Oh yeah. This lava. You want to try it, right? I want to see what it tastes like. I'm not supposed to. So have a look, right? This is molten rock. So it has the density of rock, maybe a little bit less, but it's still twice as heavy as water. If water wouldn't escape, very unlikely to get lava to escape. And as you watch it flow, fluid dynamics, you'll see that it looks just like it. You heat up rock enough, it's fucking liquid. Now, of course, it burns everything that it comes into contact with, but that's just how cool lava is, right? So this is running, oh, sorry, this is literally running lava. Good. Okay, let me show you a better one. Okay, you seen this video?
That's terrifying. I like it.
Okay. Before I play it, whatever you have inside that you're thinking about for how slow lava moves, you're wrong. Okay, this here are human beings. This is farther than human beings. So that means it's bigger.
Oh,
Okay.
Yeah.
So your expectation that lava, we just saw it was like, okay, this is going to go quick.
Like a black hole.
Yeah. So that's again in the Hawaiian island. They're just chilling. Yeah, hard hats. It's really gonna help you against lava. I'm gonna like the hard hat on some people. That's pretty amazing, right? You don't think of lava. Okay. All right, finally, last one. There's just too many cool videos of lava. And- There we go. All right, this is the drone gets hit by lava. This is my favorite part of this. You're flying over lava, and they got it back, and they looked at the fins, and all of the fins were like wobbled. Okay, so that's what kind of lava is that? Is that running? Hold on, let's go back.
Look how she funky.
So this is more explosive, right? More goopy. Okay, finally, I said last one, and then there is one more last one. This one's beautiful.
That's so scary.
Yeah, and these people don't move. What the hell? Run! I mean, great. I'm glad you got this shot for me, but come on. Okay. And of course, one thing you see in all of these pictures is outgassing. Okay? So outgassing is an important component. So the things that volcanism do, they provide material in the form of gases and dust. But most importantly, they're going to remove impact cratering, right? And they're going to deliver warm magma from the interior of the planet to the surface. Okay?
Is that like, yellow stuff?
We'll get to there, yeah. When we talk about tectonics, we'll come back to that. Very good. Okay, so what is impact cratering? And
Actually.
yeah, well, what's happening? Yeah, smashing into the planet, right? And in fact, this was really contentious for a really long time. So people looked at the moon and they saw these circles on it. And they said, well, we know what those circles are. Those are volcanoes. Right? You've seen lots of volcanoes. How many meteor or how many impact craters have you seen on Earth? What?
Not many.
Not many. I mean, one, they're really boring, but you know, they don't really show up that much. Mostly they're volcanoes. So in fact, it took many, many years. There's this long debate about what the hell these things were on the moon. And they were trying to understand, okay, so this object here, you claim, this is your claim. I'm gonna pretend like you're pro asteroid. I'm gonna pretend like I'm not pro asteroid. So your claim is that this thing was formed by an asteroid. But if you say that, why is it perfectly circular? So it has to be a circular asteroid, right? Next time you're at the beach, or next time it like rains, take a rock and throw it at the ground. What is the shape of the mark it leaves on the ground? The rock. Or if it bounces, shape of the rock. It kind of looks like this, flattened out, like an ellipse.
Yeah.
So when it hits, not just the shape of the rock, it's the fact that it moves as it's going, digs out of the hole, and then flies off. So why are they circular? You're telling me every single asteroid smashed into this from directly overhead? Seems kind of unlikely, right? What's the solution? Someone's lying to you. Me or her? Who's lying? Oh. Me. Yes, in fact, I'm lying because one thing that we didn't know about, so there's a lot of energy from these things. Okay. So it took us developing a nuclear weapon here on Earth, setting one off slightly underground, and then looking at the giant hole we created and said, oh, that looks like that, huh? So maybe one good thing happened.
About that.
So impacts by asteroids and comets are what we see when we think about impact cratering. And these are basically remnants. Okay. So let me ask you a question. Okay, this is the one you're gonna think about. And look what I had to do here. A, B, C, D. 1, 2. I was like, I thought honestly about doing 1, 1. And I didn't. Maybe I'll do it next year. Okay. How many of the above objects have impact features that can be identified today between the moon, Mercury, Mars, Venus, and Earth? Let's vote. On 3, 2, 1. Okay. We got everything from 3 to 5. You don't want to defend what their choices are?
I think, Mercury or Venus, either or it can be ruled out because they're too hot before I think that happens.
Okay.
Over.
Okay. Agree? Disagree? Anyone want to jump in here?
Isn't Mercury the planet that takes most of our asteroids, so they don't hit us?
Okay, that's a thought. Maybe there's asteroids there. Anything else?
Venus has a lot of volcanoes.
Venus has volcanoes. Maybe those get rid of impact. Anyone else?
I feel like same thing in Mercury, it kind of, I mean, it has a lot of impact craters, but there's so much heat that it kind of just like fills up the older ones. And then you'll see like,
melts them?
yeah, you'll see like a ring, and then you'll see it like filled in, so that could happen to like a majority of.
Okay, so what are our votes here? How many people? 3. Okay, so which ones do we think happen? Moon?
Yeah.
Moon, okay, everyone got moon. Mercury?
Yeah.
Yeah.
Raise your hand for Mercury. Okay, okay, alright. Mars?
Yeah.
How many people for Mars? Okay. Venus? Raise your hand for Venus. Okay, iffy. Okay, Earth?
No.
Okay, alright, interesting. We're gonna come back to all these ideas, we're gonna unpack them. I heard a lot of things that we're going to try and worm our way into our understanding, okay? So, this on the left is the picture of a moon. Our moon. And this is a picture where you see it's the bottom, the top left-hand corner is headed towards the dark side where it's not illuminated, not the far side. And this would be towards the sun. Many impacts happened soon after the solar system formed, like almost right away. Okay, and we call this period the period of heavy bombardment. We can see this in the impact cratering record, and I'll talk to you about how we can build that when we do the asteroid sizes lab. When you look at this picture though, what are the things that you take away from the picture? What do you see?
It's still.
Gets hit a lot, good. Anything else?
Different sizes.
Different sizes, okay. What? Elaborate. New, what?
They're not smoothed out.
Okay, they're not smoothed out, so would that make them old or new?
No, if they're not smoothed out, they're like, cause like the one on the bottom right. Yeah, it's kind of filled in, and then it has a bunch of little smaller ones, so the one that's filled in is the older one. And then the one that's, yeah, well, those that are not.
I like that reasoning, what about up here? Yeah, so they lay on top of each other, there's so many. That they're literally sitting on top of each other. And this is how we can get records of how old different craters are. Right? So they sit right on top of each other. What else do you see?
I guess they could be like cliffs.
Yeah, they definitely, I mean, we'll look at the shape in a few seconds. It's kind of surprising shape. They do like fall right in. Anything else?
A lot of small craters.
A lot of small craters. compared to other size craters, how are small craters? Okay, good. Another word for that? Correct? Frequent, infrequent, more frequent. What about big craters?
Not so frequent.
Not so frequent. What did I write on the thing that I was standing in front of? Yeah, I don't know if some of you already saw that, but okay, so what is happening here? So this is asteroids and stuff. On the Earth, why doesn't this happen? Why don't we have all of these around us?
That atmosphere.
Okay, atmosphere, good.
Mercury. Protecting us. For the moon. It might be Jupiter.
What's that? Why would water? Oh, because you hit the water and then.
There's no visible.
Oh, no, visible. Maybe they're all underwater. Is that what you're thinking?
Yeah.
I like that thinking too. Oh, the water would also slow it down too, right? On the company.
Volcano, like less.
And resurfacing. Okay, so I hear a lot of really good ideas here. So maybe we don't expect any on the Earth, but in fact, we do see this phenomenon all the time. What this is? Yeah, anytime you see a video and someone says, "What the fuck is this?" What is it not? It's not an alien. No. No. What's that?
Shooting star.
No, it's not a shooting star, and it's not an alien. It's a meteor. The word shooting star doesn't have anything to do with stars. You think a star came by and just hang out with us for a little while?
No, that's why. I said-
We talked about stars, right?
Is that the video from Russia where it was bombarded by?
No, but you will see that one later. Yeah, that's a really good one. Shall we, Vince?
Yes.
Yeah,
yes,
yeah,
yes,
yeah.
there.
Yeah, that's one of my favorite ones. Because that is a learning lesson for everyone. We'll get to that in a second. So this one here. No, this is. So you see in the starts in the top left-hand corner, comes into the atmosphere, burns up. How fast is it going?
18,000 miles an hour.
18,000 miles an hour, right? That's the orbiting velocity. Why does it get light?
Releasing the water, yeah.
This
So
The
it's gonna be-
atmosphere is igniting it.
Atmosphere is igniting it.
Sulfur.
It gets so hot.
It gets so hot that
It releases like.
releases light.
It's a specific color, right? So would that mean like it's like green? Like sulfur.
Well, not all of them are. Let's have a look, okay? Let's have a look at the colors we see here.
Yeah.
Yeah, so there is some orange. What's happening behind it?
Oh, it's breaking.
It's breaking up, right? So this one is big. It's breaking up. Material is being left behind it. The burning is all happening right here. Okay. Okay. How big is it?
Small.
What?
Big.
Maybe like
3 meters.
I'd say 10 meters.
A kilometer.
Feel like something like this.
Jeez.
The size of that ball, what is that, a centimeter?
Like that, yeah.
Is it like,
No? No, just a no.
50 meters?
50 meters. Okay, we got a large size distribution. We'll come back to this in a little while. 25 meters. Okay, right in the middle. What's that? What was that again? Price is Right rules. Okay. So in fact, impactors hit the Earth at speeds of around 30 kilometers per second. So we said orbiting is 18,000 miles an hour, but these things are not orbiting us. They're coming, remember that escape velocity was square root 2 larger, but these are coming with much larger than escape velocity. So what you're looking at here, 70,000 miles an hour. So you take a little rock, maybe 1 kilometer size rock, and you smash it into the surface. And then this is a cut section. And what it's going to do is it needs to turn all of that kinetic energy into something. So first thing it does is it shocks the layers of rock underneath. Metamorphism completely into something new called shocked quartz. And then it keeps going. And if you're nearby, you immediately become liquefied. The rocks just liquefy. The ones underneath, they're shocked. And eventually you get down enough that you stop the momentum. But you've transferred all that momentum sideways and out. And you've turned this into a sort of liquid, like a lava. And it goes. And so then, once you've forced the shockwave into this, it sends shockwave back, equal and opposite reactions. Right, so you shock, it pushes you right back, and it blows all of this material out in what we call an ejecta blanket. Now, interestingly enough, there are some really cool ratios here. So this is always much larger, or sorry, this is always much larger than this, right? This is a huge amount of energy. And the craters are usually about 10 times wider than the object that made them. So if you have a 10-kilometer crater, it was made by a 1-kilometer object. Okay. Now, no one knows what a kilometer is, so let's say that differently. If you want to make a 1,000-foot crater, you need a 100-foot object, right? 100-foot would be like what, this room? Yeah.
So then. So, cause I know some craters have like this like peak in the middle.
Yeah.
So then the ground also well, is it because of the energy that it behaves like liquid?
Yeah, so have you ever dropped like or seen slow motion of dropping water in? Maybe you've been to the restroom and something goes in the toilet and then the water comes back up. You ever seen that? This is the same dynamics, but imagine as it's rebounding, remember it's rock and it crystallizes. Now that would suck if that was the other example, but you get it.
Hey, I have a question.
Yeah.
If something like that is relatively smaller than like the crater, why doesn't it burn up in our atmosphere?
We'll get to that. The smaller ones, I never told you how big the atmosphere ones were, right? So the ones that we're gonna see, we're gonna get a little hint when we talk about the size frequency distribution of the ones that we see. Okay. Good question, so. Okay, let me show you the one that you should all go to here on Earth. Okay, this is Barringer crater. You can stand right there. You can stand right here. There's a path. And then if you want to, you can take a tour. And I think this is the path. You can walk all the way down to the middle. Okay, so this is a kilometer size object. You don't know what that means, but that's how big it is. Made by how big an object? 100 meters. Yeah. It's only 50,000 years old. That's like yesterday in geologic time period. So the Earth, sorry, the humans, for example, have been roughly the same for like 60 million years, like biologically speaking. So this is newer. This is newer probably than humans going to Australia. Australia. Okay, so this one's really interesting. It's really well preserved. Why is it super well preserved? It's in a desert. What's special about that?
There's no oxidation.
There ain't shit. There's no rain. Yeah, it doesn't erode. Right? And so you do see like some little streams in here, but they're not the majority. And in fact, this is a picture I took standing right here. And you can look into it and you see the crater walls. Right? They're in really good condition still. Okay. So you can go to this one. I think it takes like 7 hours. Once I get permission to do field trips with this class, I'm gonna let people come with me over spring break. But I have to figure it out.
Wouldn't that be like a natural disaster, something that big did?
This one?
Yeah.
Nah.
Okay.
Not in Arizona.
There's nothing there. I've seen something nice.
How many of it hit Albuquerque? Be like, woo.
The level of state though?
Well, depends on how big a city is. Kilometer wise, no. If it was like the town that you grew up in, Ohio, yeah. But like, this is, so for example, here's cars for scale, right? So like, that's a car, potentially even my car, right? That little dot right there, right? And this is a 2-lane road. You drive in on this 2-lane road. So that's your scale, right? And look, the crazy thing here, look at how close it came to hitting the visitor center. That's wild. Okay, you guys want a story time about this crater?
Yeah.
You fell in.
Story time for the crater or no? Okay, so here's a story time for this crater. So it's named the Barringer crater, because of a man who sincerely believed that he found this. He didn't find it. He knew this was there. And he was a miner, M-I-N-E-R.
Oh.
And he was like, this thing is so big, right? Whatever hit it probably had a lot of like interior metal in it, right? And so he was like, whatever smashed into there had to have metal. And so they had found like little tiny pieces that were like full of iron and nickel. He's like, bro, all I gotta do, buy the land up, dig right here, and I'll have tons of metal that's just sitting under the surface. Right? Pretty good idea, right? So he goes and he buys up all the land and tries to go look for this thing. Huge return on his investment, right? No, he goes bankrupt. Why?
You just know there's metal on the ground.
Well, because it all got fucking vaporized. And all he's left with is a tiny piece, and everything else is lost. So you can go, and if you go to Meteor Crater, I highly recommend it. I think the piece that's left is huge, it's like this big. But like, you can make money from that. I can get that from a normal place. But he thought like, oh, there would be like, a 900 meter size piece of iron he could pick up and then make a ton of money off of. So that's, we respect him for his audacity, because that would have been sick. Now, simply our scale here, when you look at the moon, we already talked about how far away it is and all that other stuff. This is Tycho crater. So that's the one that I showed you on Monday, in the bottom right-hand corner. And I couldn't remember the name of it. So this is Tycho crater. And look, there's a little peak, like you said. So the frozen peak. So this one looks very different, right? What's different in this picture other than the frozen peak?
Very rough.
So round.
Very rough, good. So round, good.
Round.
What size? Is that the shadow?
That's a shadow.
Yeah, okay.
A little. Is not in the middle. Exactly in the middle.
Not directly in the middle. It's a little off. That's good.
There's like a flat spot to it at the bottom.
Flat at the bottom. That's weird. If you go back here one picture, right? This is like a bowl all the way down. This one is like flat and then up in a wall, right? And in fact, that's because just like we talked about, the entire interior melts and then becomes a little frozen lake of rock. Okay, now here's the scale to consider. There's 85 kilometers, and that is Meteor Crater.
What was the previous one? What was that?
1 kilometer.
That was 1 kilometer. So you see the picture there?
Wait, what? Oh, okay.
Oh, that's it right there.
Yeah. Okay. That's the whole of Meteor Crater. That entire picture I just showed you is right there. Okay, that's what Meteor Crater looks like when you blow it up.
Dang.
So in terms of scale, how wide would the Tycho crater be if it were to happen on Earth instead? How?
Yeah, so when you get to something like the size of Meteor Crater, it doesn't care about the atmosphere anymore. The atmosphere is not very thick. If you think about the Earth as the size of a basketball, the atmosphere thickness is roughly a sheet of paper. And it punches through that almost immediately.
And at that point, that's just doomsday.
For this one,
Yeah.
we'll get to that. I like your thinking, and in fact, we're gonna get exactly to it. This is the best part about impact cratering.
If
We want to know where that line is, right? Like, when do we get scared? Right? Okay.
I think I'd be scared with any meteor.
Nah.
I was
Yeah.
Come on now.
Shoot them all down.
Is that one thing, like, not as deep as that one, the moon's more shallow?
Yeah, so technically it's more shallow because as it reforms, as that melt reforms into the ground, the width It's a lot deeper.
Why isn't that one pointing out that data?
It didn't
It
impact
melted
it.
much. So interestingly enough, if you make it to the surface and you look at the smallest ones, the smaller you are, the more bowl-like you are. The larger you are, the smaller that height is. As you reform. More energy. Good questions. Okay. Here's another one on Earth. Unfortunately, on Earth, most of ours look like this. Real boring. That's in Canada and 214 million years old. Can barely tell that it's there. What? Okay. So here's what you've always wanted to know. Okay. You have the impactor size versus the frequency. This is the current impactor rate. And to your point, mass extinction is around 1 to 10 kilometers. So over here we have meteor crater. That's called a small crater. Small crater. So meteor crater makes a small crater. It's on the larger size of the small craters, but it's a small crater. And over here, the stuff that we see daily is smaller than a meter. In fact, the object that you probably saw was probably only a few centimeters large. So maybe the size of this, especially if it's sorry. Maybe the size of this, especially if it's dense. Because the reason why you see it at all is that this exterior starts to, just imagine like rubbing it off. And as you peel off every layer, it immediately catches fire. And then you can reveal the one underneath. Right? It's like what are they called? No, Tootsie Pop. How many licks do you get at the bottom of the Tootsie Pop? That's what you're doing as you bring a rocket. In fact, is that true? Or no? I wasn't sure if that was a known number. In fact, the ones you see on a day-to-day basis, the average size or something that you just might see like while looking is probably the size of a grain of sand. The largest ones you'll see are probably the size of a pea.
A pea.
A pea, not the letter. Okay. Over here is when you start to have problems. Okay, tsunamis, no one likes that. You hit in the water, you make big wave, lots of people die. Climate change, why would there be climate change? Exactly, and what's that gonna do? Gonna cool the earth, kill all the plants, then kill all the animals, then we die. Okay? What's this one over here?
It just happened.
That's just so big we did. Okay, so over here is 100 kilometers. That would create a 1,000-kilometer crater. What would a 1,000-kilometer crater look like, by the way?
Mountain.
No.
Wait, 1,000
California.
Yeah. That'd be like eradicating like a large portion of California. That's it. Dang. All right, let me show you, okay? Has anyone ever been killed or injured by a meteor?
Yeah.
Someone that had really good bad luck. Really good bad
They
luck.
jumped in and said, watch what I can do.
In front of a meteor? I'll save you, Earth.
I don't know, but I want that on my list.
Okay, so in fact, only one person has been hit. No one has been killed that's been verified. Miss Hodges in Alabama got hit by a meteor and it bruised her hip. That's fucking crazy. Bro, this is from space and on its way in, it just misses you. How she had to buy a lottery ticket the next day.
Can you hear it like falling?
Yes, so it's moving supersonically. No, so it's moving supersonically.
Oh.
So if you're not in the way, yes, absolutely, you'll see it and hear it. But if you're in the way, it's like a bullet. It's gonna hit you before. Yeah. Also, who thinks, oh, I should jump out of the way of space? If I heard something like coming at me, I would look side to side before I look up.
Yeah.
What do you tell the medical profession? Like, what?
How? the correct terminology.
There's no code.
Okay, so even though no one, no human has ever been killed by a meteorite, we do in fact know that dinosaurs have. So this is a very accurate representation, right?
Yeah.
Okay, tell me what's wrong with this representation.
It splits in two.
Hold on. One at a time.
Only one.
There was only one meteor. Okay. Anything else?
It hasn't hit yet.
What's that? The dinosaurs looking? Okay. What did you say? The dinosaurs looking up? Anything else? I mean, we look up when we see meteors, so like, is that? We're not dinosaurs. We're better than dinosaurs? Do you think my dog doesn't look up at a meteor when I'm watching meteors?
Wow.
I think we're all derived from dinosaurs, right? No. Okay, what else are we missing here?
Wouldn't the sky be a lot more on fire?
Okay, maybe the sky would be on fire as it's coming in.
One fun there. Liquid fun.
Anything else?
There's already bones on the ground. They haven't hit yet. It's gonna be dead yet.
No.
Wouldn't they be dead because they would have burned up for like.
Okay, maybe they should already be killed by the pyroclastic flows as they come in. Anything else? This guy here's like scream. What's the biggest problem with this picture, folks? You should know this.
It's a drawing.
No, it's a photograph.
Who took it?
Not just kidding.
Wow.
Yeah.
Would the oceans be boiling because of the heat from the asteroid?
Not yet, but yes.
Barney.
What is the most when you think of a dinosaur's most recent ancestor, you think of
Lizard.
a bird. What does this not have? Birds. Feathers. Dinosaurs all had feathers.
How did you think you were gonna get that?
Sherry, you should know things. Okay. The dinosaurs are amazing. We could do a whole lecture on dinosaurs, and I absolutely would do that because they're really cool. But they should all have feathers. Yes. $100,000. Okay.
Yay.
So here's the reason why dinosaurs have feathers. Which comes first, flight or ornamentation?
Ornamentation, yeah.
Everyone likes to think that natural selection means that we were headed towards this one ideal goal, right? That you are evolving towards a perfect species. But in fact, this is a lack, you're lacking nuance in the way that we think about natural selection. Because you have a competition between natural selection and mate choice. So for example, we enjoy beauty. We adorn ourselves. We even modify ourselves. We see animals do this too. They are sexual like beings. They try to entice one another to have sex. Peacocks, great example of birds with great amounts of ornamentation. In fact, we have found fossilized skin of dinosaurs that has ornamentation. And because we know how the pigmentation works in current birds and how the pigmentation works in these, we know what it looks like, including the fact that these things were ornamented. So the modern belief is that when you look at feathers, feathers were modified scales. In fact, they are modified scales. And they later became developed for flight. That's gonna be an astronomy class. So they were supposed to have feathers. These dinosaurs would have had feathers. So remember that modified scales means scales originally comes from where? The ocean. Yeah.
So you're saying T-Rexes could fly?
No. I'm saying that similar to emus, which do not fly, they had feathers. You know what emu is? An ostrich?
So,
You know, like a big fat chicken?
so dinosaurs modified themselves? Like.
No. Peacocks don't modify themselves. Peacocks are ornamented through natural selection and mate choice. So these T-Rexes, in order to mate, would communicate to one another. They would have like ornamentation on their like, ooh, right? Oh, yeah. Oh, you look so beautiful today. Right? Okay. And of course, pterosaurs were a totally different animal. So when you see like a flying
The one that flies.
dinosaur, pterosaurs, like a pterosaurus, you ever heard that? Yeah, that's a whole different class. It's not a dinosaur.
Do you know what their lifespan was?
We can't go, okay, we can't do the whole lecture on these, but there's so many things wrong with these. Okay. Let's reorient ourselves. So how'd they die? I know, I have to tell people that because I feel like people don't know it enough.
You're doing a service.
We're doing a survey.
Okay.
And the important thing to consider here. So this thing smashes into the earth. Kills all the dinosaurs. Okay, no one cares. Mammals, great. Rise of the mammals, little shrews. We evolved from little shrews. Okay. Closest relative of a whale is the
What?
horse.
What?
Horse and whale linked.
Well, that's why.
What? Oh yeah, hippos. Yeah, hippos and horses are very close in length, right?
See that one.
So people were like, okay, all these fucking dinosaurs died, and it looked like they all died off at like about the same time, and then the mammals came, they started doing all sorts of wonky stuff. Why did all these dinosaurs die? How did we know that this thing even happened? It was like overnight in geologic speak. All the fossils, you're looking through the fossil record, you see fossil evidence of mammals, fossil evidence of mammals, fossil evidence of mammals, and then dinosaurs, and just really, really small mammals, and then only dinosaurs. Yeah.
The rocks.
What about the rocks?
Couldn't you see like, kind of like rings of a tree, like how?
You can see the ages, yeah,
Yeah.
but how did they know that there must have been an impact? Yeah.
Theorize that like the Gulf of Mexico is where the meteor actually impacted.
So that's one step further, we're gonna get to that, but how did they know to look for an impact?
I would say probably the type of dirt or dust that the meteor kicked up from the place of impact spread all over the world.
Right. So interestingly enough, so someone said, hey, listen, something killed all of these dinosaurs at the same time. And let's do the same example again, where you don't believe anything I say. And you're like, that's bullshit. No, like they just died off because they got tired of eating. Right? And I say, no, someone killed them. And someone killed them from outer space. And you say, that's crazy. What do you think, aliens? I'm like, yeah, aliens.
Yeah.
And I say the evidence for aliens has to be they all died at the same time. Because when I look in that fossil record, in that layering, there is a weird element just in this layer for about this long and never again and never before. And that's called the KPG boundary. And what you find with the weird element is, anyone know what it is? Sulfur. Your dust, not an element. Not sulfur, we have that here.
Whatever element.
An element that's not here on Earth?
Yeah. So what I said was, we don't see it anywhere after, and we don't see it before.
Okay.
And we see it in a giant layer.
Thank you.
Iron.
We have lots of that, we have lots of that. You've heard of it, it's in the elemental.
You're ready.
Okay, germanium is like a fun one, that was close.
California?
No, California. Iridium. Yeah, I know, why do they not have, the only place I need it is like right there, and it's never in the chart of elements. So iridium is commonly found, but usually it's quite heavy and it sinks into the mantle. And so you don't find it in the crust. We don't find it around us. We can get it in small amounts in order to play with it and do like science stuff. But this is just the layer around the whole planet. And they knew isotopically that this happened at this time, date coincidental with the death of the dinosaurs, and they found this on the entire planet. So the first place that they looked at for the KPG boundary was in, I think, I want to say Colorado, but I think it's actually like Arizona. So in the Rocky Mountains, you can see the Rocky Mountains themselves were once underwater. That same land was underwater. And then the Rocky Mountains pushed it up, and it shows the entire seabed, exposed seabed, and you can see that layering. You can walk up to that layer, and you can be like, oh, it's right there. And it's like slightly white rock. It's fucking sick. Okay, we'll talk about that when we talk about tectonics next week. So you said, okay, now we have to go look for where this thing is. So how the hell do we find it?
Whenever you find that element, it's like closer,
Okay, we find it everywhere.
it's like 3 times more of it.
I know, but we find it everywhere.
So you look for a big hole.
You look for a big hole, okay, good, I like it, that's the right answer, look for a big hole, okay, so we go looking for a big hole, we can't find it, what do you do?
Maybe it's in
Okay.
the ocean.
What? Maybe it's in the ocean, very good idea, maybe it's in the ocean. Okay, so that is the Chicxulub crater, you see it?
Yes.
Well, it's a circle that I drew on top of it.
Wow.
Come on now, don't be mean to me, you see it now?
I'm hard there, I see a heart.
What? Yeah, I was just gonna say, you fly in here, you drive down here. And little did you know, this is where all the dinosaurs died. Okay, so where is it? It's here, right? Do you see the crater now?
Yeah.
This is the crater rim. And it's ridged. Okay, and in fact, you can find it even better with this. So what is that?
The thermal temperature.
Wasn't that like how high up?
It's the same color bar, but we don't know how to use good colors in science.
That's like the how high up thing.
That like especially for specific metals?
So notice what we're looking for here is that it also goes into the water.
Or size of it.
This is actually mass concentration. So there is more mass here. Okay, there's less mass than the average, there's more mass than the average, there's way more mass than the average. And if you look, you can see concentric circles from the place that it struck. So as it hit, blew out, and it created concentric circles. They're called the mass concentrations. And what you're looking for there is places where material was stuck together really hard. You find them by flying a spacecraft. Okay, so that's what killed the dinosaurs. It looks like that. Pretty cool, right? So as it comes into the atmosphere, you have no time to react. The image of those dinosaurs looking up and like watching it go by. If you've ever watched like Don't Look Up or any of these films about something coming into the into the atmosphere, they're all wrong because you don't get to go, oh my goodness, go tell my wife I love her, right? It's bang, right? And in fact, that's what you get here. It punches through the atmosphere in just a few seconds. Remember that it's moving at something like 70,000 miles an hour. And the atmosphere itself is 500 miles. So you do the math. Yeah,
So they didn't even have a chance to look at it before it impacted.
probably not.
Was it like super bright?
What do you mean super bright?
Did it look like the?
So, okay, so let me talk to you now about what happens afterwards. So the things that you see here, first it slams into the planet. There's the recoil from the drip, right? And what you see here, this shape, this is the ejecta blanket forming. Now, because this is an atmosphere, you punch through the atmosphere, but the atmosphere then has to respond. And so it starts to get out of the way. As the atmosphere gets out of the way, it is both very hot and moving very quickly. And so basically, if you're standing right here, you're killed instantly, just from the sound. The sound collapses your chest cavity, you can't breathe, you're dead. Your entire body is destroyed. So everyone around here is already dead right away. And then out here, the shockwave, maybe it's a little bit nicer, but it's really hot. And so you die from how hot it is. Okay. And so maybe you're out here. So this becomes first a boiling wave of tsunami, and then it cools down enough and it's just a normal wave, but it's just gonna drag you away. But my favorite part, absolute favorite part. Okay. This ejecta starts going up. Up, 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 up. And it's gonna come down again because gravity. So you have what are called secondary explosions. So what you end up with is objects about the size of Mount Everest flying up on intercontinental ballistic trajectories and landing on other parts of the Earth and creating secondary craters all over the Earth, smashing into the Earth, creating secondary sets of explosions, creating secondary tsunamis. And that's why we can't look for like, oh, well, this iridium is everywhere. Yeah, the whole fucking planet got destroyed. Of course, I mean, this is like, the whole planet's fine. Everyone lived, except for all the dinosaurs, right? And so then, of course, what happens is after all these explosions, like you said, all the dust is left there. It chokes out all of the light for the plants to grow. Some plants can definitely survive, but something like 90 to 95% of all species die. And the ones that do survive tend to be like shoe-like guys, like walking around in like rat caves and stuff. And they're like, we're getting worms. And then they evolve us.
Any words?
Fucking cool, right? Yeah, question.
With the impact of the crater, how would it affect sea life?
Yeah, sea life is chilling.
Didn't they have their own mass?
Well, the impact of the crater doesn't have a problem, right? Because they're underwater. So you have a tsunami, everyone in the water is chill. But what happens is, where does the life in the seawater come from? The sun. And if I black out the sun, the algae starts to die off. The things that eat the algae, like the kelp, start to die off. So you have a different mass extinction. But that's not just from the impact, that's from the dust. Does that make sense?
Yeah.
Yeah, when I say mass extinction, I mean everybody did.
It just has to be like 1 kilometer, no, 10 kilometers above, right?
100 kilometers.
No, 1 kilometer.
Let's go back. I don't know what I wrote. Mass extinction is slightly larger than a kilometer. Probably like 5 kilometers. Because 5 kilometers makes a 50-kilometer hole. So meteor crater would have been bad, but like not that bad. You know, like meteor crater is like a.
You know how big the meteor was that killed off the dinosaurs?
Yeah, it was like this big. I'll find out. And also people say, well, maybe it wasn't just one, and this is really hard to tell. Because we can actually, when we have an impactor, we can usually assign it to a body that it came from. This is like what Laura Whitney does, or Dr. Whitney does. She looks for asteroids and tries to put them into classes of like where they actually originally came from. So as they're orbiting, multiple objects can hit us. And maybe one of them hits us, but one of them stays behind. And people think that maybe this is just the one that we know about, but that there's one just over here slightly in the water that we can't see, you know, or been reformed. Pretty cool, right? Okay. We have a tiny bit of time. What do craters tell us about surface age? Totally different question. Oh, sorry. Any other questions about exploding dinosaurs?
No.
What do craters tell us about surface age?
How old is it?
How old is it? But which way? Presence of craters means
Surface hasn't reformed since they got here.
so the surface is old. Right? So that's exactly the right way of thinking. You start off with this idea. I see a lot of craters. That means the surface hasn't changed much since it was created. That means it's old. Right? Okay. So compare the numbers of lunar impact craters in the dark, the lunar maria, versus the highlands in the light. Which surface formed more recently? So here is the two that you're going to compare. Dark stuff to the light stuff. Let's have a look-see with your eyeballs. So is it A? Oh shit, I did 1. The highlands, 2, Maria, 3, we can't tell. 4, they're both the same age, 4.5 billion years old. Let's vote on 3, 2, 1. Good. All right, almost perfect. It is the Maria. Maria's older, sorry, Maria's younger because less craters. So I look in this region and there's like none. I look in this region, there's a lot. So the highlands must be older than the Maria. And in fact, that makes sense. If I punch into this and I make this, like let's say it's this originally. I punch into it, I make it all liquid magma, and then it reforms. Right? So the lunar Maria is a kind of annoying volcanism impact cratering because it's a little bit of both. So if you look at the moon and you say there's no evidence of volcanism, you're wrong, because that is evidence of volcanism. But it's also evidence of impact cratering.
Is there any active volcanoes?
No.
Excuse me.
No, very, very dead. Died almost right away. Formed, died geologically.
When we went to the moon, did we land near Mario, or was it all just like on the crater?
Yeah, we went in and dug a bunch of different places and we wanted to try all their different rocks. And I'll, you know what, I'll put a little map. And I'll show you all the places. It's kind of cool. Okay. Oh, that's fucking useless. Okay, so less craters means younger surface. It means the surface has been repaved since the period of heavy bombardment. However, it does not mean that it's a younger planet. Okay, I'm going to propose to you a question, and you need to think about this one. If you already know it, and you just like watch this video, don't shout it out. Think about it. Okay? If the humans died, we all died. In 50 million years, what evidence would there be that we existed? Keep in mind, the Earth is moving around, volcanism. We have materials that are strong, some that are not so strong. Bones. So bones, totally going to be disintegrated by that. There's no 50 million year old humans. Not over 50 million years. I mean, maybe we're fossilized. Maybe.
Plastic,
What?
plastic,
Plastic will definitely be gone.
hopefully.
Totally disintegrated.
Would it be high levels of pollution in the sediment layers?
I love the pollution. Ooh, I like that. That's a pretty good one. They'd be like, what the fuck happened here? They were burning all kinds of shit. Yeah, suddenly this spike in nuclear waste. That's a really good one. That's not one that I thought about. That's one that I'm thinking of, but
Would it be our satellites?
you know that already?
No,
Because we're talking about the moon, that would be very reasonable. In fact, that would be the best evidence. So in fact, the moon is geologically dead. Mercury is also geologically dead. And there is a footprint on the moon. There's several. In fact, when I have that same map, I'll show you that you can use a telescope. You can look at the place where the flag is, including the place where the lander is.
They would have to look at the moon for them to know that we were here.
Yeah. The best evidence of us in 50 million years is a footprint. Okay.
Unless the moon gets better.
Yeah, unless it gets blurred. But the interesting thing is, in this footprint, when did we land on the moon? 67. So why has it not been?
There's no wind.
There's no wind. There's no volcanism.
There's no rain.
There's no rain.
Why does the flag stay up?
Why didn't the flag stay up?
Why does it stay up?
The flag didn't stay up.
It doesn't stay
It
up.
fell over when we flew away.
But-
What did it do?
No, it's like the actual flag.
There's a rod in it.
Okay, thank you.
Why did it fall down?
It was, they didn't put it down properly.
Waves from the 15.
To get off, we had to fly off. And then just like when we leave the earth, we make this big plume of gas as we fly away.
How did we further?
I know, it's not very smart. It blew over.
That part.
I mean, they were like, when they got off, they're like, let's go, boys. And then they got back on and they're it fell over.
You're gonna go back.
Back home, they're like,
Okay, so we're gonna talk more about this. I'll show some pictures. We'll start on this one, and then we're gonna look at cratering on nearby planets. Any questions?
You see the footprint that don't?
No, No, I don't think so. You have to have really, really tight angular resolution. I don't know if we have that. Maybe we'll try it. Put that into your notes. We'll try and look at the footprint on the moon. I don't think we will be able to see it.
Is the footprint on the right side or the left?
Light side. Hold on. The near side.